Suppose I have a little yellow ball hanging on a spring. At first, it is at rest, so that's the rest position. Then I decide to pull it down. By some distance, x. Maybe not x. I just decide to pull it down and let go, so it goes up and down. So at a certain point in time, it might be say there. It might be there. Okay, with attached to the spring, and it might be on its way up, just swinging back up and down again. Okay, so let's say that the displacement at this point in time is x. Now I want to write down an equation for the x in terms of things like velocity, time, acceleration, and force. I know that the force is upward. There is an upward force. Going upwards, and it's going up and down. Okay, so I know that. I also know the relation between the force and the distance, the displacement. So F is actually equal to a constant times x. We know this from Hock's law, for example, and we know that the pendulum has a similar relation. Right, now let me write down a name for this kind of motion. Let's say for the pendulum, the force on the pendulum bob is proportional to displacement, and it's also the same for the spring. And we'll actually find many examples in physics and actually in real life where we have this oscillation, where oscillations follow at least approximately a relation like that. Right? When something goes back and forth, it often happens that the force that wants to pull the object back to its rest position is proportional to displacement. Now, so this kind of motion, this kind of oscillation, in which force and displacement are related in this way, they have something in common in the way they move, and there is a name given to this kind of motion. It is called simple harmonic motion. Now we might use the word SHM. You might want to use this short form when referring to it. This is such a long 3 words. Okay, simple harmonic motion. And let me write down the a proper definition of this type of motion. The simple harmonic motion, is one in which a body moves under a restoring force. Okay, maybe let me be more precise. It moves under a force, okay, that is proportional to its displacement. So in this case, x is the displacement, f is the force. Okay. Now, but that's not all. Okay, that's not all. The force is proportional to its displacement. If we just say that, it means that if, let's say, the displacement is downward, the force is also downward. But that's not true. We see that the force must be opposite to the displacement. It's proportional to its displacement, but directed in let me just write but in the opposite direction. Okay, so that should do. That should do for most purposes, I hope. So if I displace it one way, like down, force must be up. If I displace it up and let go, the force must push it back down. So you see, I've added in an additional detail that is not obvious from this equation. From this equation, we can see that the force is proportional to x, but it doesn't tell us about the direction. But in this description, I've added in this important piece of information that the force must be in the opposite direction to its displacement. And it's the same for a pendulum and for many types of small oscillations. Okay, so from this result, what I like to do now is to write down, rewrite this in terms of acceleration. I want to rewrite the force in terms of acceleration. So since we're talking about displacements and we're talking about directions, let me be very careful and define the directions properly. So we are talking about motion along a straight line, so we don't have to use vectors explicitly or directly. What we can do is we can define directions, because along a straight line there are only two directions, right? In this case, down, and up. So as we've done for earlier topics on velocities and acceleration, I can define one direction as plus and the other as minus. So in this case, I'll just choose the downward direction as plus. Okay, so I have directions. So by looking at the signs of the x and f, whether they are plus or minus, right, by looking at the numbers, I can tell the direction. And I can now what I can do is this. I can make this equation more precise. I can take into account the direction in a very simple way. I can go to the equation and simply add a minus sign. There, it's that simple. Just by adding a minus sign, I would have included this bits of information that it is opposite. So you see, this definition actually translates directly into the equation. If you look at it, you have it talks about displacement, which is x. It talks about force, which is f. It talks about proportional, which contributes to the k, the constant number that multiplies x. And it talks about opposite, which gives the minus sign. Okay, so it is important to understand how this equation can actually come from this definition of a simple harmonic motion, and conversely how the equation can give the definition. So they are very, one is the same as the other, and the other is the same as this. Okay. So right, what I want to do next is to further rewrite this in terms of the acceleration. Now we know the relation between force and acceleration, because according to Newton's second law, force is equal to mass times acceleration. So therefore, I can replace the F here by ma. So if I substitute this into this, I'll get ma is equal to minus kx. ma is equal to minus kx. Now, if I now divide both sides by m, I'm going to rearrange this into a more common, more standard form that you see in textbooks. Okay, this is what you get. So this is okay, this is fairly standard. Now, an even more standard form that can also be used for other examples like pendulum and other things is to do something else. Right? Is to rename this k over m. Rename k over m as this symbol, this omega squared. So this is like a W with rounded bottom. Right? It's our Greek letter omega. So it's to rename this as omega squared. Now the reason why we want to rename this as omega squared, I will explain next time. But for now, just take it that it's just a renaming in this case. So at the moment, no new physics, nothing new. So I'm just going to write this out again and write it as a is equal to minus. So I renamed k over m as omega squared. So that's my new name for k over m. And now I finally get a form that is very standard. That is a very, very standard form of an equation for a simple harmonic motion.